Thank you. And so my talk is not going to be nearly as exciting as the previous speaker. It's much more focused, a simpler problem. So I'll be talking about inducing distributed representations for multiple, for words in multiple languages at the same time. And this is joint work with Professor Titov and his graduate student, Binod Bataray. So I don't really need to motivate why distributed representations are important. Seemingly large section of the papers in the last 2 years in NLP conferences has distributed representations or word embeddings in their titles. But let me just say a few words. So NLP systems treating words as atomic symbols need a lot of annotated data simply because of sparsity issues. So vocabularies tend to be large and they grow. There are always new words that are getting invented and added to the vocabulary. So one way of dealing with this is to, instead of using words as atomic symbols, is to try to represent them as some sort of in some sort of alternative way. So typically people use cheap data to induce these word representations and then pass them as features to learning algorithms. So by cheap data, I mean typically unannotated texts in a given language, so you can go and crawl this on the web. So what are our options for these representations that we could use instead of words? Well, the first idea is to try to use clustering. And we can go and cluster words over a given corpus, and then use cluster prototypes instead of individual words as features in the learning algorithm. So there are multiple issues there. One is how do you choose how many clusters? And also, what does it mean to have a good clustering? Multiple clusterings are possible, and deciding which one is better is not that trivial. Another option is vector space representation. So until recently, that really meant representing a word given its as a context in which it appears. So typically, you have a small contextual window that you use to collect other words that tend to co-occur with a given word, and then you turn that co-occurrence information into large vectors that are of size of your vocabulary, so very large sparse vectors. And then you define some sort of distance metric in that space to try to understand how similar words are. So the issues there is that these tend to be tend to use heuristics. So what exactly you put in each one of the variables in your vector tends to be kind of algorithmically, heuristically defined. And then there's a third recent, relatively recent type of representations, and those are distributed representations. So the idea is to use vector space models, but then add some statistics, some machinery there to actually induce and learn them. So the advantages of those that they're as compared to vector space models, they tend to be low dimensional, and they're learned, and they could be learned for a given task. So, and this is, as you can guess by the green boxes there, that's the focus of this work. So, what we'd like to do is to actually learn these representations, distributed representations, from multiple languages at the same time. So, the idea is that you sort of end up in this, mapping these words in two different languages in the same space, where semantically similar words end up being close to each other in that space. So, one kind of reason why you would want to do that is when you have two languages and one of those languages has annotated data for a particular learning task and the other has no annotations. So imagine you can train in the first language and then directly take your classifier and then directly apply it to the same classification problem in the second language where you have no annotated data. So let me start by sort of introducing a hand-wavy kind of a summary. So we want to induce this mapping from words to vectors, and we'll use cheap monolingual data to do this individually for each language. So these are fairly standard techniques now. So you go and collect a bunch of data in English and German on the web, and you induce these representations. But the additional trick is we're going to use a little bit of additional data, parallel data, which is sentences together with their human translations, to essentially bias these representations to be closer to each other for words that are translations, and hope that sort of the rest of the space ends up kind of bringing similar words together across the two languages. So as I mentioned, the goal is to make sure that to end up with words that are close to one another if they're similar. And the intuition, or the kind of the idea that we use is we treat this as a multitask learning task problem, and we treat individual words as tasks, and task relatedness in the MTL sense is defined by the co-occurrences in the parallel data that I just mentioned. So that's basically the idea. So in the rest of the talk, let me start with giving some background on multitask learning, in particular one formulation that we use, and then brief review of neural language models, models that have been around since early 2000s, and then sort of marry them together to build the cross-lingual representations. And then I'll show some very much of a kind of a toy experiment at the end. So generally speaking, the goal of multitask learning is to improve generalization performance across a set of tasks by learning them jointly. And the idea is, as you learn them jointly, you share using a shared representation. And kind of the intuition there is that, as you sort of let the information propagate across multiple tasks. So for some tasks for which you have no or little annotated data, you get benefit from related learning tasks. So a very particular setup that we're looking at is MTL setup proposed a few years ago by Klementiev et al. And the idea there is that you have k-related tasks, and each one is, you try to learn a classifier parameterized by v sub k, and you try to minimize this objective here. So if you forget the second part of the sum, it's simply you basically have a sum of objectives of the k subtasks. So if you don't have the second component, if you basically go and learn them independently, you're done. But then there's this additional piece here, which a regularizer, which prefers to learn parameters, to induce parameters v sub k's to be similar to each other for tasks that are related, as defined in the interaction matrix A. So this is the parameter that I'll talk about later. So I'm glancing over notation here, but basically the idea is that you want to prefer v sub k's to be closer to each other for tasks that are similar to one another. So this sort of naturally applies to what we're trying to do. So our idea is we're going to use it when we learn word representations. Our words are going to be tasks, and we're going to steal this regularization part of the regularizer part of the objective for inducing our representations. So I just want to say that I'm going to talk about one particular way of inducing monolingual distributed representations next, but this trick doesn't apply only to that, so it's just kind of a general idea. Okay, so moving on to the next piece of the background is our neural language models. So this was introduced in 2003 by Benjo and et al. And the idea here is that you have a simple feed-forward neural network that you use to estimate a language model. So what happens is you have a short context of a few words, usually 5 to 10 words, which serve as a signal to predict the next word coming in the word sequence. So you have, in this particular sentence, the previous words are slap, the green, and you're trying to predict the next word. So what happens there is each one of the context words is, so there's a shared representation C, and each one of the words is mapped to an index in that lookup table. So the first step of the process, each one of the words gets looked up in the lookup table, converted into a real k-dimensional vector, then concatenate it. So if you have you're only looking at the context of 3, you'll have 3 of those vectors concatenated together. Then you apply linear transformation in the hidden layer, followed by some nonlinearity, and then your output layer sort of separates out the classes of meaning the types of the next word coming in the sequence. So your output layer is as large as your vocabulary, and the idea is that it estimates the probability distribution of the word coming next in the sequence. So presumably, the value for the word, the element corresponding to word which is going to be high here, if I learned it correctly. So the key component here is that shared representation C for us. And an important an important side effect of learning these neural language models is that this d-dimensional representation C has the properties we're after. So it captures semantic properties of context words because they tend to be predictive of the next words that are coming in sequence. And it tends to induce, exactly has the property that we'd like, so it tends to induce words that are closer to each other for in the embedded space if they're similar to one another. And so the important part is that the embedded representation C is learned as part of the backprop, and the learning maximizes the standard language modeling objective. So you're basically trying to estimate C together with the rest of the parameters of the network using the standard objective here. So then we can put the NLM, the neural language model idea and the multitask learning idea into the same objective, and that's exactly what we try to do. So what we're doing is we're now proposing to train 2 language models separately using large monolingual data sets in each one of the 2 languages. And then we'll use the extra multitask learning regularizer to make sure that the embeddings we induce sort of get bridged across the 2 languages as we train. And we'll use this interaction matrix A, which I defined a few slides ago, to tell us about relatedness of words across the 2 languages as we learn. So if we put it together, the learning objective looks like this. So all of this I already talked about, but just to rehash. So this is the first part is language modeling part, except now we're doing it we're summing over 2 languages. And the second part is the MTL regularizer, which prefers Cs to be similar to each other for words that are related. And so that part basically ensures, the first part ensures intralingual properties, and the second part lets us bridge these across languages. So there's nothing special that we do to train this. So we use stochastic gradient descent, and the only kind of point here to make is that every time we make an update to the context words as we train, we also make an update to words in the other language that are related to it. So each update step is substantially more expensive. Yeah, sure, sure, sure. Yeah. It's the representation that we learn in. Yeah. 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 So kind of to rephrase it, so the idea is that you have examples in both languages, sequences of words. You have sort of a moving window that you look at previous context and you try to predict the next word. And every time you predict, you update the context words, but you also update words that are translations of those words in the other language at each update step. So you make updates for the other language, even though you're looking at an example in the first language. So A is something that we set ahead of time. So I'll mention that actually on the next slide. Yeah. Okay, so that's exactly the answer here. So so the idea is there are more details on the paper. I'm really just glancing over this, and there are more elegant way to define A. But basically, the idea is that as I mentioned, A is the interaction matrix and defines relatedness between tasks, which are words in the two languages. So what we're going to do is we'll take parallel data. So these are sentences and their translations. We'll use standard machine translation tools to induce word alignments. So those are basically alignments between words and likely translations in the other language. And then we'll count them up and we'll say that the more alignments we get for a pair of words, the more related we are, the fewer we get, the less related they are. And we'll use that to directly define A inverse, which is what we need for computing the updates. So, sorry?
Is this symmetrical or asymmetrical?
Yeah, so, right, so you have words in one language as rows and words in the other as columns. So we don't explicitly define similarity within the language because we sort of assume that the language modeling part is going to take care of that itself.
I mean, I guess I'm saying is like, is the relatedness of A to B the same as B to A?
Right. Yeah. So the way we do it here is that so alignments are asymmetric. So what we do is we run it both directions. We take an intersection and we assume that it's the same.
Thank you.
But yeah, it's a simplification. All right. So let me just say a few words about experiments. We have we're building 40-dimensional representations of words in English and German. We use fairly standard data sets, the RCV Reuters data sets. For monolingual corpora, and we'll use Europarl data that Jordan mentioned to define the interaction matrix ahead of time. And we'll do two things. The first thing is we'll take a handful of words and we'll just look to see at neighboring words that we induce in both languages and see what it looks like, and then we'll run a very sort of toy example of document classification and to see if the cross-lingual embeddings that we induce are informative in this direct transfer setting that I mentioned in the beginning of the talk. So let me show you a couple of examples. So here I just picked a handful of words in English, and I looked at the nearest neighbors in the induced embedding in both English and German. So I didn't really have to separate them in columns, but I just did this so they're easier to read. So you see that the nearest neighbors to January are the 10 months in both English and German. You see that the verbs in both languages closest to word said sort of relate to vocal transfer of information, informed, stressed, declared, etc. And then some things don't work so well. So these words next to oil should probably represent something like industrial sector words, and some of them fit and some of them don't. But yeah, so that's kind of one way to visually check to see if it makes sense. And then the other toy experiment is So here's what we're trying to do here is, thank you. We have this representations we induced. Then we're going to use them as features for multilingual document classification tasks. So we'll assume that we'll have training data in one language and no training data in another language. So we'll train a simple classifier to decide between 4 categories of these documents in language 1, and then we'll take that classifier and apply it directly with no training data on the same feature space in language 2. So that's the blue line as a function of number of training examples. And then the 2 baselines are train a classifier in language 1, use either a statistical machine translation system to translate from L2 to L1 and then classify, or simply gloss and then classify. Glossing just means dictionary lookup, so simple translation. So, and then the dashed line here is the majority class baseline. So, so the point was basically just to see that the features we induce are informative in this cross-lingual setting. So let me just move on to the summary real quick, and I won't read it. I don't have enough time, but thank you.
Let's thank the speaker.